Good day, students. Welcome to part one of the New York Regents High School exam for geometry, the August 2012 release test questions. Remember, this document is accessible online on the New York State Education Regents website. Okay. All right. Let's go ahead and take a look at question number one. So question one says in the diagram below of circle O, chord AB is parallel to chord GH. Let's indicate that chord AB is parallel to chord GH. Chord CD intersects AB at E and GH at F. So these are the points of intersection. Which of the following statements must be true? So anytime you see two parallel chords in a circle, there is one theorem that automatically comes to mind. Let me share that theorem with you, and that will make it easy for us to determine what the correct answer to this problem is. So anytime you have two parallel chords in a circle, okay, it doesn't really matter what their lengths are. The requirement is that they're parallel. So let's say this chord is parallel to this. They always intersect congruent arcs. Okay, the arcs intersected are always congruent. So this is x degrees. Guess what? This angle right here is going to be x degrees also. All right. So anytime, let me make another sketch. So let's say we have another set of parallel lines here, like this, and like that. Guess what? Um, this these angles intercepted here by these two parallel arcs. Let me try and make this one parallel to that one. Make it parallel as best as I can. So let's say that this line right here is parallel to this line. Guess what that means? They're gonna intercept congruent arcs. So this were y degrees. Guess what? This side here will be y degrees also. Okay. So taking a look at this problem, since these two arcs chords are congruent, are parallel, then they're going to intercept congruent arcs. So guess what? This arc right here is going to be congruent to this arc right here. Okay? So we can conclude that arc AG is congruent to arc BH. Okay? So that's the rule for parallel chords. So let's see which one agrees with what we just found out. AG congruent to BH is option 4. All right, so don't forget this cool idea. Okay, let's move on to number 2. It says the vertices of a parallelogram ABCD are 2, 0, 0, 3, 0, negative 3, 3, negative 10, and 5, 0. If ABCD is reflected over the x-axis, how many vertices remain invariant? Invariance is just a fancy way of saying it doesn't change, remains exactly the same, okay? So when we reflect about the x-axis, what happens? When we reflect about the x-axis, all you have is just the opposite of the y-coordinate, right? Let me give you an example just to illustrate. So let's say I had a point, a random point, 2, 1. So 1, 2, 2, 1. Now, if I reflect this point about the coordinates are 2, 1. If I reflect this point about the x-axis, it's going to go straight down, a mirror image down, and it's going to become 2, negative 1. Okay, so there you have it. So what do you notice here? A reflection about the x-axis just basically means you're taking the opposite of the y-coordinate. Okay, and the reflection about the y-axis means you're taking the opposite of the x-coordinate. Okay, so whatever axis you're reflecting along, you do the opposite of the other axis. So if I reflect ABCD about the x-axis, what's going to happen to this point? So let's say ABCD, we have A is 2, 0, and B is 0, negative 3, C is 3, negative 3, and D is 5, 0. So if I reflect about the x-axis, what I'll do is I'll negate all the y's. You see all the y coordinates here? I'll just simply take the opposite of the y coordinates, okay? So if I take the opposite of the y coordinates, the coordinates that remain unchanged, those are the ones that are invariant, okay? So let's go ahead and do that. So let's say the reflection is going to be A prime, okay? A prime will represent the reflection. So A prime is after reflecting downwards. We're going to have 2. The opposite of 0 is 0. And then B prime, if I reflect downwards, 0 stays the same. The opposite of -3 is +3. And then C prime, which is a reflection downwards. The x stays the same. We do the opposite of the y, which is +3. And then D prime, the x stays the same. We do the opposite of 0, which is just 0. So which of these coordinates match with the original set of coordinates? Those are the ones that are invariant. So how many of them? These two are exactly the same, and these two are exactly the same. Okay? So what's the rule here? The rule here basically is as follows. If a point is on the x-axis, it's right on the mirror of reflection. So when you reflect about the x-axis, it has absolutely no effect on it. Okay? Notice 0 is its own opposite, so it doesn't change. Okay, so that's why we have 2 points that are 2 vertices that are invariant, and the 2 vertices that are invariant makes option 2 our correct answer. Okay, so just a real quick point note. If you want to reflect along x-axis, reflect along x-axis, you negate the y coordinates. Okay, and then if you want to reflect along the y-axis, what do you think you do here? You just basically negate the x coordinates. Okay, in this case we're reflecting along the x-axis, so we negated the y's, and whenever y is 0, that basically meant that the point was going to be invariant, or the vertex. Okay, all right, so there we have it. All right, moving along to question number 3. You said n is the midpoint of AB. The coordinates of A are -3 and 6, and the coordinates of M are -5 and 2. What are the coordinates of B? All right, so basically the midpoint formula is basically the average of the 2 points, right? The average of the x and the y coordinates. So the midpoint formula M is given by x1 plus x2 over 2, comma y1 plus y2 over 2. Okay? To be more specific, let's specify what our midpoints are going to be. Let's write it as a coordinate. So I'm going to call this the x coordinate of my midpoint, and the y coordinate of my midpoint, x of m and y sub m, equals the average of the x's, x1 plus x2 over 2, comma y1 plus y2 over 2. Okay? So let's see, what do we have here? We have point A is going to be x1, y1, the first pair of coordinates. B is going to be x2, y2. And then M is going to be x sub m, y sub m for the midpoint. Okay? All right, so let's see. In this problem, x1 is going to be -3, and y1 is going to be 6. Okay, because that's the first point, x1, y1. All right, and then x2 is for this, so this is for point A. And then for point B, x2 we do not know, and y2 we do not know, because we are asked for the coordinates of B, so we don't know what the coordinates of B are. But we know what the coordinates of the midpoint M. All right, so M, x of M, x for the M is going to be -5, and y of the M is 2. Okay, so we don't have to do too much in this problem. We can just focus our attention on the x coordinates, okay? Because you notice all the x coordinates and your alternatives are distinct. So I can just focus on the x. If I can get the x correct, that will be my answer. So what this is telling me that is that if I average the x's of A and B, I'm going to get -5. Okay, so let's set up an equation. Using the x's, I know that the x-coordinate of my midpoint is going to be the x-coordinate of the first point plus the x-coordinate of the second point divided by 2. Okay? I know that the x-coordinate of my midpoint is -5. The x-coordinate of point A is, let's see what it is -3, plus the x-coordinate of my point B, which is x2, I do not know, divided by 2. So if I can solve this equation for x2, then that will tell me what the x-coordinate of B is, and that will be the answer, okay? So this is an algebraic equation. To solve this, I'm going to multiply both sides by 2 and add 3 to both sides, okay? All right, so let's do it. So multiply by 2 both sides. So you're going to have -10 equals -3 plus x2. And then you simply add 3 to both sides. Add 3, and you have x2 equals -7. So which of these coordinates has -7 as an answer? It's option number 4, okay? We can do the same with the y's, but that's not necessary because we already have a unique x result. Had it been that we had an overlap, let's say we had a negative here, then we have to do the y piece also. Y of the m is equal to y1 plus y2 over 2, and then we actually have to go through the whole process and solve it. And if we do solve it, we're going to end up with -2, and that will make 4 the correct answer. Okay? You can go ahead and verify that if you want. All right, let's take a look at question number 4. It says when a dilation is performed on a hexagon, which property of the hexagon will not be preserved in its image? So if something is not preserved, that means it changes. Okay, so let's go ahead and take a look at 2 hexagons. So let's say this is the first hexagon we have, and it got dilated. When it dilates something, you're altering the size. You either make it smaller or you're making it bigger. Okay, so let's dilate it like this. So there goes the second hexagon. So let's take a look at these two. What changed under dilation? Dilation basically means you're altering the size. Okay, so what does that mean? It basically means that the lengths are getting bigger. So if you look at this circle, see how small that, see how that is? This side is much smaller than the other side, okay? So the lengths have been increased by a certain factor, okay? How about the other things? Parallelism is the fact that the opposite sides are parallel. If you look at this smaller, I'm gonna call this H hexagon, and then this will be H prime, okay? This is the original, and this is the image, H prime. So if you look at the sides, this side is parallel to that side, okay? And then that side is parallel to that side, and then this side is parallel to this side. Is that the case here? Absolutely. Parallelism is preserved under dilation because this is parallel to that. The top is parallel to the bottom. And this side right here is certainly parallel to that side. Okay? So we already know that this is the answer. I'm just trying to show you that the rest are the same. Orientation is exactly the same. They have oriented in the same way. Measure of angles, absolutely. Okay? To illustrate that to you, let me show you something. So I take this right here. You see how that angle matches with that? That angle matches with that. That angle matches with that. That angle matches with that. Okay, for a hexagon, if this is a regular hexagon, for example, all the angles, you can figure exactly out what your measures are. Okay, so definitely the angles are preserved under dilation. Okay, and they're congruent. So everything else is preserved. The only thing that changes is the length. When you dilate an object, you're changing the measure of the side lengths or the size of the shape. Okay, so the answer is option 3. Okay, let's take a look at question 5. It says, as shown in the diagram below of triangle ABC, a compass is used to find points D and E equidistant from point A. So basically, use a compass to draw your arc right here. Since this is congruent to that, you can call this R1 and R2. These 2 points are equidistant from here. Okay. All right, and then Finally, a straight edge is used, I'm sorry. Next, the compass is used to find point F equidistant from point D and E. Okay, this point right here. Finally, a straight edge um, is drawn, is used to draw AF. The point G is the intersection of the line and AF and side BC of triangle ABC is labeled. Okay, so which of the following statements is true? So if you take a look at this statement right here, this procedure is basically the procedure for bisecting an angle. Okay, if you already know how you bisect your angles, this is exactly how to bisect an angle. Okay, so the correct answer is that AF is a bisector of angle BAC. Okay, so this is angle BAC right here. Angle BAC, AF is bisector. In other words, this angle right here is congruent to this angle right here. These two angles are congruent. Okay, so if you have your your bisection of angles algorithm memorized, you should automatically know that this is how you bisect your angle. Okay, well, let's assume that we didn't know how to bisect their angles. Can we use some postulates for triangle congruence to show that this angle is in fact congruent to this angle? Absolutely. Let's just connect this side right here and connect this side right here. Okay. We know that AF is congruent to AF, right? Segment AF is congruent to segment AF by reflexive property. And by construction, we know that, so this side is congruent to itself, that's an S. And by construction, we know that AD is congruent to AE, so this side is congruent to this side. By construction, AD is congruent to AE, right? And then also by construction, we also know that DF is congruent to EF. By construction, DF is congruent to EF. So what do we have here? We have side, side, side. So using the SSS postulate, we know that these two triangles are congruent. Okay, triangle ADF and triangle AEF implies that triangle ADF is congruent to triangle AEF. Okay, and since these two triangles are congruent, what do we know about corresponding parts? We know that corresponding parts of congruent triangles are congruent, so that follows that this angle BA, angle, we can call it BAG, or let's call it DAF, angle DAF is congruent to angle BAF. So this angle is congruent to that angle. And guess what? Angle DAF is the same thing as angle, it's the same thing as half of angle BAC. And then angle EAF is half of angle BAC also. So since these two triangles are congruent, that means that AF actually bisects your sum. Okay? So there you have it. All right, so the correct answer is that is option number 2. AF is the bisector. All right, let's move on to question number 6. So we are asked to, considering this, we have to find a measure of angle JSM. So this is JSM right here. This is what we're looking for. So to figure this out, we're going to do this step by step, okay? I'm going to look for, since we have a bigger triangle here, I'm going to look for angle A first. And then after I find angle A, I'm going to try and look for angle B. Okay? I'm going to find angle A using the triangle angle sum theorem, the fact that the sum of angles in a triangle is 180. I'm going to look for angle B using the linear pair postulate, knowing the fact that the sum of angles in a straight line is 180. And then I'll use the triangle angle sum theorem to find this angle right here, angle JSM using the triangle angle sum postulate, which states that the sum of angles in a triangle is 180. Okay? Alright, so triangle angle sum theorem. So let's go ahead and do it. So let's find angle A first. So to find angle A, let's focus on triangle JEA, the bigger triangle. Okay, triangle JEA. So to find angle A, I know that 180, which is the sum of the interior angles of a triangle, is equal to angle A plus 48 plus, this is the right angle, plus 90 degrees. Okay, so I'm going to have 180 equals A plus, if I add these two together, I'll have 138. And then I'll subtract 138 from both sides. And I'll have that angle A is 42 degrees. So guess what? This angle right here is 42 degrees. All right, we need one more angle, so we can use the triangle angle sum theorem to figure out what triangle JSM is, okay? So I need to figure out angle B. Now, angle B is a linear pair with SME. So the measure of EMS is 59. So let me box this. So to find angle B, using the linear pair postulate, I know that angle B plus 59 degrees from a linear pair, which is 180. So angle B, so B is simply going to be what I get when I subtract 59 from both sides. So I subtract 59, and I end up with the fact that angle B is 121 degrees. Okay, so this angle right here is 121. Okay, so let's figure out the last one, angle GSM. I know that angle GSM is one of the angles of a triangle, and we know that the sum of interior angles of a triangle is 180, the triangle angle sum theorem. I know that, let me box this before I continue. I know that from the triangle angle sum theorem, angle A plus B plus the measure of angle GSM, these are the three angles of a triangle. Interior angles, they add up to 180 degrees, okay? So how do we get GSM? We just add A and B together, subtract from both sides, and that gives us angle GSM. We know that angle A is 42 degrees, what we found earlier, and B is 121, plus the measure of angle GSM will give us 180, okay? All right, so let's see. If I add these two together, I'm going to have 163 plus the measure of angle GSM. GSM equals 180. So let's just subtract 163 from both sides. Subtract 163, subtract 163. Let me write my GSM properly. Sorry about that. So subtract 63 from both sides, and then we're going to get the measure of angle GSM. If you subtract 163 from 180, you have 17 degrees equals 17 degrees. Okay? So our answer is option 4. All right, moving right along, question 7. We're told that EB and EC are drawn, and AB is congruent to CD. So this side is congruent to this side. Which statement could always be proven? Okay. All right, so let's say that this AB is 5. If AB is 5, CD is 5, right? And let's say BC is 2, for instance. What can we prove right here? AC is congruent to DB. Is that the case? Is it true that this entire length is congruent to this entire length? Absolutely, because we know that this two sides are already equal. So if you add the same measure to them, you're going to end up with the same thing, right? So AC, if you look at this example that we have, AC is equal to 7, okay? And DB is equal to 7 also. Okay, because these two sides are congruent, so when you add this on to both of them, you're going to end up with the same result. So the answer is option 1. All right? Okay, let's take a look at question number 8. All right, so given a proof here, using side, 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 as we can see, to show that these two triangles are congruent. And then the next step, step 5, is the conclusion that angle B is congruent to angle D. What's the reason? Well, anytime you finish a proof using any of the triangle postulates, SSS, ASA, SAS, or AAS, which is the same thing as SAA. Anytime you use any of these postulates to complete a proof, the next line is always that the congruent parts of congruent triangles are congruent. Because you have already established congruency using one of these. This already establishes congruency, okay? So anything you want to say after it is that you have to use Cpctc for short, of congruent parts of congruent triangles are congruent, all right? So notice the proof has been completed right here. So here is going to be Cpctc, all right? So what do we have here? We can just simply say corresponding parts of congruent triangles are congruent. Okay, because you already established congruency in step number 4. So your answer is option letter 3. Option number 3. Alright? So keep that in mind. Okay. Number 9 says the equation of a circle with its center at -3, 5 and a radius of 4 is. So the equation of a circle with center HK and radius R is given by x minus h squared plus y minus k squared equals r squared. Okay? So what you always do is you take the opposite of the x and the y, you insert it here, and you square the radius, okay? So let's do that here. X minus, you do the opposite. What's the opposite of -3? +3, right? So plus 3 square plus y. You take the opposite of 5, which is -5, square equals, the radius is 4, so you square that. 4 squared is 16. So which of these equations match this right here? So we can clearly see that the only one that matches is option number 3. Okay, so please, please, please do not forget to square your radius also, or else you'd have made a mistake of selecting option 1. You always take the opposite, and then you square your radius for the equation of a circle. So there you have it. All right, let's take a look at question 10. It says in the diagram below, A, B, and CD intersect at E such that AE is congruent to CE and angle BCE is congruent to angle DAE. Triangle DAE can be proved congruent to triangle BCE by, okay, let's see what we have here. We're told that AE is congruent to CE, so this side is congruent to that side. That's an S, that counts as an S. You're also told that angle BCE is congruent to DAE. BCE is congruent to DAE. What does that count as? That counts as an A. What else do we know? If you look at this triangle, you notice that these two sides intersect in a special way. They form something. You know what they form? They form vertical angles, okay? And what do we know about vertical angles? Vertical angles are congruent. So this angle is congruent to that angle right there. So guess what? That is another A. So if you follow the order, what do we have here? We have ASA. Okay, so ASA is sufficient to show that these two triangles are congruent. Okay, so the congruency postulate we're going to be using here is ASA, angle, side angle. All right, so there you have it. Remember, the last piece is because of vertical angles. Vertical angles are what? Congruent. The other two congruencies were given. Okay, this was given and this was given. So we have S given, the A given, so we have ASA. Alright, so there we have it. So thanks so much for taking the time to watch this video. You can feel free to subscribe to my channel by clicking up here. And if you like this video, you can click like down here. And please, please, please post a comment down here in the comment section and tell me what you think about this video. More clips can be found on Mathgotserved.com. Congrats again for taking the time to study. I hope you do well on your Regents exam. Thanks and have a wonderful day.